that you understand the difference between a vector measurement and a scalar measurement, let's go ahead and take the next step in our study of kinematics. Let me ask you this question. What is the difference between distance and displacement? Do you know the difference? Well, there's a big difference between the two, and it's important to understand it. The reason it's important to understand is that these two words come up all the time in the study of kinematics, in physics and physical science. Distance and displacement. So in order to understand this, let's just take a look at some examples. Let's first of all take a look at some examples of distance. Let's suppose that you start at point X. We'll call that point X. That, by the way, has a name. That starting point has a name. It's called the origin. And we're going to start at the origin, point X, and we're going to ride a bike or some other mode of transportation all the way over here to point Y. And we're going to stop at point Y. If I were to ask you, what is the distance that you traveled? You might have measured the distance and you might say, well, between point X and point Y, I know I traveled 10 kilometers. And that is the distance between point X and point Y, 10 kilometers. Well, 10 kilometers, that is a scalar measurement. So the first thing you want to remember about distances is that distance is a scalar measurement. It does not have a direction. Distance does not have a direction. It's a scalar measurement. And it is simply the length of the path traveled between the origin, your starting point, and your ending point, in this case at point Y. So I could say here that the distance I traveled was simply 10 kilometers. Well, let's take a look at another situation. Let's suppose again you started at point X, our origin, and you traveled all the way to point Y, right there. And then you turned around and you came halfway back and stopped right there. We'll call that point Z. If you stop here at point Z, the distance that you traveled, the total distance that you traveled was 10 kilometers to Y and 5 kilometers halfway back to X. Z places you at a total distance of 15 kilometers. Why? Because that is the total length of the path that you traveled between the origin and your final destination, which was point Z. So the distance you traveled was 15 kilometers. Now let's take a look at a third situation. Let's suppose that you started at point X again and you traveled all the way over here to point Y. Now that was a total, remember, of 10 kilometers. And then you turned around and you came all the way back home again to point X, to your origin. And that trip gave you a total of 20 kilometers round trip. The distance that you traveled was equal to 20 kilometers, the round trip distance. Okay, let me throw another situation at you. What if you started here at point X and you walked through the woods on this path, which was very curvy, very convoluted, it wasn't a straight path, and you came all the way back here to your origin right there at point X. You came right back home again. Now if you measured the length of that path around all these curves right through the woods here, you might find out that the total distance that you traveled was perhaps 20 kilometers, whatever it was. Distance, by definition, simply put, a simple definition, distance is the total length of the path that you travel from your origin to your final destination or stopping point. It is the total length of the path traveled. That's distance. And distance is a scalar measurement. Going back to the previous lesson, remember that distance is a scalar measurement because it has a quantity and a unit of measurement. That's all it has. That makes it a scalar measurement. So distance, here's what you want to remember, is the total length of the path traveled from the origin to the ending point, and it is a scalar measurement. Now let's take a look at displacement, and we'll use the same scenario each time. So in the first scenario, we started at our origin, which was point X, and we traveled all the way over to point Y, and that was a distance of 10 kilometers. But the displacement is not just 10 kilometers. The displacement in this case is 10 kilometers east. Displacement, unlike distance, is a vector measurement. It is a vector measurement. And that's important. It is a vector measurement because it not only includes a quantity and a unit of measurement, but it also includes a direction, in this case east. And you'll notice right over here I have a small compass rose over here. It shows you north is towards the top of this page, south is towards the bottom, east is to the right, and west is to the left. So displacement will always include either a stated direction or an assumed direction. So if I said somebody has a displacement of 10 kilometers, then you have to just assume, even though I didn't tell you what it was, that there's a direction there somewhere. So let's take a look at some other situations. This first situation, the displacement was 10 kilometers east. In the second situation, we started at X and we traveled all the way over here to Y. Then we turned around and we came halfway back. Now, if we look at the distance is a total of 15 kilometers. But the displacement, when you reach this point, point Z, right here, when you reach point Z, your displacement is not 15 kilometers. Your displacement is equal to 5 kilometers east. And you might say, well, why is that so? Well, it's the real difference between distance and displacement. Your displacement is the straight line distance and direction between the origin, your starting point, and your ending point. So this red line represents your displacement, and that displacement is 5 kilometers east of the origin where you started. That is really the difference between distance and displacement. Distance is simply the length of the path that you traveled, where displacement is the straight line distance and direction between the origin and your final ending point. So let's take a look at this third example down here. We started at X and we traveled all the way to point Y, and then we turned around and we came all the way back home again to our original origin. And when we did that, the distance we traveled over here on the left, the distance we traveled was a total of 20 kilometers. That would be from X to Y is 10 kilometers, and from Y to X back again is another 10 kilometers. So the distance was 20 kilometers. However, our displacement is now 0. Why is it 0? It's because we are back at the original point and we are not displaced from that origin. Displacement, going back to the definition, is the straight line distance and direction between the starting point, the origin, and the ending point. And the straight line distance and direction between the starting point and the same point where you end is now going to be 0. So the displacement is 0 in this situation. All right, let's take a look at this next example down here. We walk this curved path. And I won't redraw this path, but let's take a look at this. If we look at the distance that we traveled along this curved path over here, we traveled a total distance of, I said, 20 kilometers. But since we came all the way back to the original origin, our original starting point, the displacement is equal to 0. Why is it 0? Because displacement is the straight line distance and direction between the starting point and the ending point. Another way to say this is how far and in what direction you are displaced from the origin. So in the first situation up here, let's take a look at these three. In this first situation, your displacement is 10 kilometers east because you are displaced 10 kilometers east of the origin. In the second scenario, you are displaced 5 kilometers east of the origin. And in the third situation down here, because you came all the way back to your original starting point, your origin, then you are displaced 0 kilometers from your origin. And that is the difference between distance and displacement. All right, now we'll take a few minutes. We'll see if you understand what we're talking about here, the difference between distance and displacement. Here's a situation I'm going to give you, and I'm going to ask you a couple of questions about it. If you start right here at point X, there you are, and you walk 20 meters over here to point Y, and then you turn south and you walk 10 meters down to point 0, and then you turn and walk 20 meters west towards point Q, and you stop right there. Your origin is at X and your final destination is at Q. My question for you is, in this trip, what is your distance and what is your displacement? Go ahead and figure out what each of these are. Stop the video, solve the problem, then turn the video back on, and I'll go over this with you and see if you got it right. So go ahead and pause the video now. Alright, now that you're back, let's go ahead and solve this. The distance that this person traveled, remember, is the total length of the path traveled. That would be 20 meters plus 10 meters, which gives you 30 meters, and then 20 more meters, which is a total of 50 meters. So the distance this person traveled would be 50 meters. Now, what is this person's displacement? Remembering, of course, that displacement is how far and in what direction you are displaced from your starting point. And that is represented by this line right here. This would be your displacement. And your displacement in this situation looks to be just about 10 meters south. In other words, you are displaced 10 meters south of your starting point, of your origin. And so, there are the two answers: distance 50 meters and displacement 10 meters south. So far in our study of kinematics, we have talked about vector and scalar measurements and the difference between the two. We've talked about distance and displacement and the difference between those two terms. And now we can take this study of kinematics to the next level, and we can look at, really start to understand what kinematics really is, the study of motion. And the simplest way to study motion is to look at the speed of an object or its velocity. So it's going to be really important here to understand the difference between speed and velocity. And it might sound a little strange, but speed and velocity are not the same thing. although in some situations they might seem like they're the same thing. Given the situation, they can be totally different. And you might not understand that right now, but when we start solving speed problems and velocity problems, you'll very quickly see how these two can be very different from each other in some cases, and yet very much alike in other cases. It just depends on the situation. So let's first of all, let's take a look at a couple of very simple definitions. The definition for speed is simply rate of motion, and the equation that's used to calculate speed really illustrates that. The equation that's used to calculate speed, specifically average speed, and that's an S with a line over it, average speed is equal to the rate of motion. That means the change in distance, or delta D, over the change in time, or delta T. And you see that triangle that I put right there, that is a Greek letter delta, and it simply means change. So as an object moves, its distance changes, and that changes over time. Time also changes as the distance changes. And if you look at the relationship between the change in distance and the change in time, you can calculate the average speed of an object as it moves from one place to another. It's rate of motion. Now, how is speed different from velocity? Well, velocity is rate of motion in a given direction. So there's one difference right there. And the other difference that you see really doesn't show up in this definition, but it really does show up in the equation that can be used to calculate velocity. So the equation for velocity looks like this. Average velocity, that's a V with a line over it. The line tells you that's average velocity, is equal to displacement, or change in x. And you might think that D would be used to represent displacement, but in physics or physical sciences, the x is used to represent displacement, and this says change in displacement divided by change in time. And right there in front of you is the real difference between speed and velocity. They both include change in time, but speed is change in direction over change in time, where velocity is change in displacement over change in time. And why is that important? Because when you look at an object's displacement, that makes this velocity a vector quantity. Velocity is a vector quantity. It includes a direction. Why does it include a direction? Because it's calculated with displacement rather than distance. Speed is not a vector quantity. Speed, because it utilizes direction in the equation. Speed is what's referred to as, again, a scalar quantity. And that is the ultimate difference between speed and velocity. Speed is calculated using direction, so speed is a scalar quantity, a scalar measurement, while velocity is calculated using displacement, and that makes velocity a vector measurement. And that's the difference between the two. All right, now we're going to spend a little bit of time talking about this equation that we have for speed and also the equation that we have for velocity, and we're going to solve some problems. Use the velocity formula, V equals d over t, or V equals delta x over delta t, to solve problems related to both speed and velocity. Now, in order to do this, we're actually going to break these equations down. We're going to use two different equations here, one for speed and one for velocity. We're going to simplify this equation and use for velocity, we're going to use v equals x divided by t. And remember, of course, that the x actually stands for displacement and not distance. For speed, we're going to use simply speed equals d over t. So if you have a problem that asks you to calculate speed, you're going to use distance in the calculation. If you have a problem that's going to ask you for a velocity, then if you have a direction, you're going to use that direction because displacement includes a direction. And you'll probably understand this a little better if we go through a couple of problems that illustrate this in a graphic sense. So let's just look at a scenario here. Let's say we have a car, and this car is going to travel down the road. And let me put a road in here. There's our road. The car is going to travel a distance, D stands for distance, a distance of, let's say, 20 kilometers. So the car is going to travel a distance of 20 kilometers. And let's give it a time here. Let's say that the time it takes this car to travel this 20 kilometer distance is, how about 0.5 hours? That sounds about right. That's a half an hour. 0.5 hours. So if we calculate the speed, we're going to use this equation. Speed equals distance divided by time. And because, you know, the car speeds up and slows down as it travels from one point to another, it might not be traveling at a constant speed. Speed might actually change a little bit. Then we have the total distance and the total time. So really all we can calculate is an average speed. So to indicate that, I'm going to put a line above that S. So this now says average speed is equal to distance divided by time. It comes from that first equation we talked about. Average speed equals change in distance over change in time. We just kind of simplified it here. And so the second step is to plug in the numbers and the units from this problem. So the numbers here is 20 kilometers. That goes to replace that D. And then underneath that is the time, 0.5 hours. So the average speed, when we work this out, it works out to 40 kilometers per hour. And that's the average speed of the car. Now let's go ahead. We're going to calculate the average velocity. Well, the equation looks pretty much the same. It just says average velocity equals not distance, but displacement x over t. Now here's the important distinction here. The displacement has a direction, and if there's any way you can get the direction, you want to use it. In this problem, the car is moving, it looks like, towards the right hand side of the paper, and by convention, when you look at a map, north is at the top of the paper, south is at the bottom, west is to the left on the paper, and east is to the right. So this car is traveling east. So here's the situation. When we plug the numbers in here, we have average velocity equals displacement, not distance. And the displacement x is equal to 20 kilometers east. Now in a word problem, it might just be stated. In a diagram, you can always use the direction that the arrow, the direction of the car, or whatever the object is that's pointing. So this is 20 kilometers east. And so we're going to say that here. We're going to say 20 kilometers east. Divided by the time. Well, the time doesn't change. It's still 0.5 hours. And so the average velocity of this car is 40 kilometers per hour east. The E stands for east. And there you can see illustrated the absolute difference between speed and velocity. Speed of the car, look at this, 40 kilometers per hour. Velocity of the car, 40 kilometers per hour east. The difference is that direction. Remember that speed is calculated using distance and velocity is calculated using displacement. And that makes speed a scalar measurement, while velocity is going to be a vector measurement. Alright, let's take a look at another problem, and as we go through this, working the problems will help clear up any questions that you might have. So make sure that you pay attention and work through the problems with me. In this case, we're going to start out with a car again. We're going to have a car here, and that car is going to be traveling down the road. And here's our road right there. And we're going to say that, well, from the origin where the car starts to the end of the road over here, looks like, well, let's just say 20 kilometers. And so here's the situation. Our car is going to drive out here 20 kilometers and then turn around and drive halfway back again, right to there. So halfway back. If you look at that, that means that the total distance traveled, we'll call that D total. Just like that. The distance total. The total distance traveled for this car is 20 kilometers over to here, and then halfway back would be 10 kilometers back towards home or wherever the origin is where the car started. So the car is going to be traveling a total distance of, it looks like 30 kilometers. And let's give this a time. Let's say that the total time is equal to, let's give it 0.75 hours. That's 3/4 of an hour. So there's enough information to calculate the speed of the car. So let's go ahead and calculate the speed of the car. Well, we come over here and we know that speed, average speed, is equal to distance divided by time. That's change in distance over change in time. And we can plug some numbers in here. Average speed then is equal to the distance, which is 30 kilometers, divided by the time, 0.75 hours. And we work that out, and that gives us 40 kilometers per hour. There is our speed, 40 kilometers per hour. Well, let's do something different now. Let's calculate the velocity of the car, just as we did in the last problem. Calculate the average velocity. And average velocity, if you recall, is displacement delta x over delta t. So displacement over time, not distance over time. Does that make a difference here? Well, watch this. What is the displacement of this car? Well, remember the definition for displacement. The definition for displacement was the straight line distance and direction between the starting and ending points. Another way to say that is displacement is how far the object, in this case the car, is displaced from its origin. So the car drove out here 20 kilometers and came back halfway and stopped right there. So the displacement is represented by this line right here. This is the displacement. And that displacement, if you look at it, is 10 kilometers. Because this car is where it stopped over here, is now displaced 10 kilometers to the east. There's the E for east. 10 kilometers east of its origin, of its starting point. That's the displacement, 10 kilometers east. So when we go back here and calculate the velocity, the average velocity is displacement, which is 10 kilometers east of the starting point, and then we get x is 10 kilometers east divided by the time, and of course the time didn't change, it still took 0.75 hours. And so the average velocity of this car works out to be 13.3 and that's repeating, and that is kilometers per hour east. And there again, very clearly illustrated, is the real difference between speed and velocity. The speed, 40 kilometers per hour, that's a scalar measurement. The velocity, 13.3 kilometers per hour east, that's a vector measurement. It has that direction. Another thing I should point out to you, to make sure that you remember this now, is that in this situation, whether or not you call this speed or velocity is exceedingly important. Look at the difference in the answers. The speed is 40 kilometers per hour. It's the total distance divided by the time. Whereas the velocity is displacement divided by time, which gives you a totally different answer, 13.3 kilometers per hour. So there is an important distinction between speed and velocity.